because if you look at here, this is some kind of a V shape. Okay? We look at here, this is some kind of a V shape. So you will rotate at the point origin here. Okay, but you'll find that is the center of gravity for this V-shaped objects here is actually somewhere here. Okay, that's why actually if you watch any explanation video there are of central gravity, they will tell you that center of gravity not necessarily on the objects. It can be in the middle of the A. Right? So similar to this case, we have a V shape here. The center of gravity is actually in the middle of the A. It is not on the object itself. Okay. So if we break this part into two parts here, so one over here, the red line, then maybe we have another one I draw with a blue line. So if we break into two components here, then we can find two different central gravity. So this is for the part 1, this is for part 2. So then we'll have two mass and its radius of the mass to the center of rotation. So this one we call it R1. So over here we call it R2. So we will get this diagram, this part first. Okay. So if you look at here, this is actually the centrifugal force mr omega square, or actually is the ma radial. Okay. So r omega square is a normal acceleration. So we call it r omega square. Okay. That's why if you try to find the force ma, so we can write it as m1 r1 omega 1 square. Okay. So same thing happened here for the other force. So it's the m2 r2 omega square is actually the mass multiplied with the acceleration in the normal direction. So it will give us the what we call it the centrifugal force, right, when we rotate. So if you look carefully here, the centrifugal force here is highly rely on this omega. That's why when your objects turn at a very slow speed, so the effect of this centrifugal force is very minimum. But when its speeds go up, then you will start to have more and more impact to your system. Just like you can, if you don't mind, you can then do an experiment in your home also, but you may have to make sure you are safer. So you can put a small plasticine, very, very small, don't put too big. You stick your plasticine on your table fan, and then you run it at the speed 1 and compare to speed 3. So you will find out how much is the vibration that it will contribute to your fan. Okay. But the one has to do very in a safe manner. So that is how you can visualize the impact of this, the omega, right? The angular velocity of the system that actually contribute to this centrifugal force, and then this force is the one who caused the unbalance. Okay. So that's why we have a centrifugal force here. We have another one here. So how are we going to do the balancing? Right? So that's why we have to put a equivalent amount of centrifugal force on the opposite direction. Right? So in this case, we don't. There is a lot of way you can do it. So maybe one of the way is if you are allowed to put a lot of balancing weight. So one of the way you can do it, you just put the identical M2 here and R2 here. Then put another one, identical one, the M1 and R1. So it will be balanced. But this is not the engineering way. Okay. So for engineering way, we we just want the minimum way to balance it, so we can balance it with a single mass. So as a MB, the balanced mass, the RB, the balance, the location of the balanced mass, and then it will contribute this MB RB omega square, which has to counter these two unbalanced force, right? So once we get this and this, then we can design a proper geometry to fit into the system, okay? So we can fit this here. So then that's why when you look at some rotating parts, you will see that there is a part of material actually doing nothing. Seems like doing nothing, right? No, what we call it, the geometry function, right? Means this part actually doesn't serve any geometry function, right? So it didn't do anything physically, but what it did is to balance the force on the other side, right? Okay, so in the diagram we have, so we can model it as a 2-point mass M1 and M2 concentrated at its local center of gravity. So, and then we let the third balance mass MB to be added at some location at the RB in order to satisfy equation 3.1. So what we'll do is we have the equation just now. Okay. So we have a M1A normal 1. Alright, so it's M1A1 plus M2 or minus that because the equation we have is summation of force minus MA equal to 0. That's why there is a minus. So there is no external force given. So this is 0. So that's why we have minus M1A1 minus M2A2 minus M3A3 equal to 0. Okay. So in our case, we don't call it M3, we call it MB and AB. Yeah. So that's why we have this M1R1 omega square, M2R2 omega square, and MBRB omega square. But right there is a 1, 2, 3. Yeah. Because these three mass now, it will actually rotate at the same omega. That's why we remove the 1, 2, 3 here, right? So what happened is then we can divide everything by omega because omega is the same parts here. That's why we will remove the over here. We'll be able to remove the omega in the equation from the equation. Okay? So we will left with MBRB equal to minus M1R1 minus M2R2. Okay. So don't just to remind you that don't confuse with your understanding, right? Because this one seems like the equations to find the central gravity. Yeah. Okay. If you ever if you still remember how you find the central gravity, this is the one. Okay. But for balancing, actually this is this one, or we can call this is the correct equation. So that's why we are not saying you do a summation of MR. You're actually doing the summation of the centrifugal force in the system, right? But just that all the force here has the common omega, then we drop the omega, so it looks like the mass radius products. Right? This is the original that we have to solve. Right? You don't just focus on this one. By right, we have to focus on the top equation. So because this R is a vector, okay, so it consists of X and Y component. So that's why then we can break it into the X and Y component, right? then we can have the x component here and the y component here, right? Because basically we also have these two to solve. We have to solve these two value, right? Once we have MBRBX and MBRBY, then we can find the location, the data, right? The angle where it should be, right? So in this case, is where this one has to be located. That's why I call it theta B, right? So again, when we draw this, we have to fix the axis. This is x, this is y, okay? So we fix the axis. So so the RB is it can be found from this formula, square root of RBX squared plus RBY squared, and MBRB, right? We can find it, right? There's the whole thing, the MBRBX squared plus MBRBY squared, and then square root the whole thing. Huh? So we'll find this, right? Same things here. Yeah, we just write. This is basically the same. I just write it in different way. Okay. So sometimes don't confuse with the multiple equation is being written there, but basically they are only one equation here, right? So theta B is the angle at which the balanced mass must be placed. MBRB is has a solution with the infinity number, right? Because any combination between the MBRB will serve the purpose, right? So normally in a physical case, it's depending on whether you have the space to put your balancing mass, right? Because for example, now if we find out the MBRB, MBRB is 1 kg meter, right? So you can define RB 1 meter, then your MB will be 1 kg as well, right? But the problem now is maybe 1B is too large for you. Your system cannot accommodate mass at the 1 meter radius. Then I can choose the MB is 0.5 meter. Then your MB will become 2 kg. So it will still serve this purpose, right? So that's why it depends on whether you can take more weight or you can take more radius, right? So for example, a fan, okay? For example, we have a fan, okay? If you want to do balancing, so basically you can put the mass along this, right? So that's why you have a flexibility in terms of your radius here. So where you want to put it, right? But sure, you cannot put more than whatever available from the blades. That's why your R is limited to the length over here, right? Then you can define how much weight you want to put in. So let us look at one of the example here. So we still refer back to the diagram we have just now. So now it gives some value to us. So we have M1 is 1.2 kg, M2 is 1.8 kg. And then the radius given is 1.135 meters at the angle of 113.4. So if you go back, yeah, this is 113.4 degrees. So it measures from the XY axis. So we have R2 is 0.2822 at the 48.8 degrees. So what we can do, we break it into the X and Y component. You see it's very similar to what we done for the dynamic analysis. So we can we have to find the XY component. So we find the R1X, R1Y, R2X, R2Y. Then we have these two equations. Okay. So that's why now, because we are solving the same problem, so we can use this formula straight away. But if for you, you better remember this one, right? Maybe I move to here. It is good that you remember this one, right? Summation of force minus MA equal to 0. So depending on how many mass is given, in this case it's only 2. So plus the balancing mass, then it will become 3 component. That's why we have 1, 2, 3 component here. So then we can substitute the value. M1 is 1.2 kg, and then this is R1x, and this is M2 R2x, right? M1 R1x, M2 R2x. So then we have M1 R1y, M2 R2y here. So then we can find the value for the MB-RBX and MB-RBY. Right? Then we substitute in order to find the angles. Right? So if you do the calculation, 0.433, right? If you make the if you press the calculator, right? This is something I want to highlight here. For example, now you press the calculators of this value. What actually you get? Right? You actually get 79.62. You won't get this number over here. Right? Because what the system will calculate is, right? It will give you just a second. It will give you this angle when you calculate it using the formula. Okay. Accidentally press. So this is X, this is Y. So when we calculated this, it will give you this is 79.62. So as I mentioned that, there's a second, someone commented R1X. Oh, okay. R1X is negative 0.451. So sometimes when I type the lecture note, it will be missing things. Okay? So there is a minus here. So it's missing here. There's a minus. Thank you. Right. So thank you for highlighting. Right. But sometimes I purposely don't change it. So then you read few more time. Right. So at least with that, then it show that you really read and try, right? Because I know that a lot of you will just read and not try. You must try, and then when you start to notice there is a problem, then you will understand better, right? So you must try. So we have this 79.62, which is given here, but when we specify the angle, we always specify the angle from the x-axis at the counterclockwise. That's why then you have to take the 360 minus 79.62. Wait. Hey, sorry. This is negative, then I'm doing it wrong. Here. Negative, it should be here. Then this is 79.62. at the theta b. I keep accidentally press the button. X and Y here, because both are negative, the X component and the Y component is negative, so it's here negative. Negative means it's here. So the angle that we are getting from calculator 79.62 is here, theta b. Right? So now if we measure the full angle, what we need is we take 180 plus 79.62. So that is where we get the 259.62 degree. So you can see that it's using these numbers. All right. So your calculator, however you press, it will never give you more than 90 degrees. Yeah. So that's why you have to. That's why I always encourage. Once we have this number, you sketch. Even for myself, I will sketch to find out where is the angle that given by the calculators. Okay? The calculator will give you the angle measure from the horizontal line. So if they are at this place, so the angle given to you is this one. So if they are in the sector 1 here, so the angle given to you is there. Right, then this one will be the answer. But for sector 2, the angle given is over here. Then you will take 180 minus the angle that we calculated. Right? So that is important to understand it. Okay? Then we can find the MBRB. So this is MBRBX, MBRBY. So we'll find the value of 2.402. So MBRB will not have negative. Okay? You won't get negative value. You are not going to get negative value. So it will always be positive value. Okay? Because it's a scalar, it becomes a scalar unit. So MBRB, we call it the mass radius product. So now it's 2.402 kilogram meters. So then we can identify, okay, what is the radius to be. Since this question doesn't give MB, so that's why you can make any assumption, right? Or is given the radius. No. So basically, this question doesn't give you specifically what is MB or RB. So in this case, it take RB as 0.806 meters. Right? So then we can calculate the corresponding mass MB here. So we have 2.98 kilogram. Okay. Means that 2.98 kilogram at here, and then we will put this 2.98 kilogram at the 0.806 meters apart. Okay. So should be not that difficult. I think you touched on this before, maybe in your maybe in your foundation or your physics. Okay. So then we can move on to the dynamic balancing. So just now static balancing we say is one plane, single plane balancing. So when we go to dynamic balancing, we call it two plane balance. Okay, two plane balance. Right. So there is two criteria to meet. So the first one is the summation of force equal to 0, which is same as the static balance. Same. So we add on one more, which is the summation of moment is equal to 0. So this is to fulfill the dynamic balancing criteria. So we can look into this. Okay, so now we have this you can see now what happened here is when we are in the dynamic balancing or two-plan balancing, you will find that the unbalanced mass, it will not stay in the approximately same position on the Excel. So just an example here, if my M2 here, if my M2 moves to here, right, then I can treat this problem as a single balancing and then add another balance mass at this plan. So then I will solve. So I just use static balancing. The problem now is the M1 and M2 are stay at the different location along the axis or the axle of the rotation. So then we must solve this using dynamic balancing. Right? So they involve moment. Right? So the same thing happen when there is a mass rotating. So it will create this centrifugal force. So we have M1 R1 omega square and another centrifugal force M2 R2 omega square. So this is the side view. So just like that, these two force now is at the opposite direction. So if we set this is the x-axis, so we will say that the M1 is at the 90 degree, yeah? And then M2 is at 270 degree, okay? Because we measure from here 90, we measure from there 270, okay? So this moment act in plan that include the axis of rotation of assemblies such as the XZ and YZ. So the moment vector of direction or axis is perpendicular to the assembly axis of rotation. Any rotating object relative to long in axial direction to the radial direction. So you can see this ratio, axial and the radial. Then we have to dynamic balancing for it is needed for complete balance. Okay. Figure 12-2, statically balanced. Okay. So as I mentioned here. So if my M1 equal to M2, R1 equal to 1, 2, if you look at this, they are static balance because this force is equal to the force at the bottom here. Okay, so statically they are balanced, right? But when we look at the moment side, then they are not balanced. So to balance dynamically, for example, automobile tires and wheels, okay, there's a two correction plan. They are inner and outer edge of the wheel rims. So counterweight are needed at the proper location based on the measurement of the dynamic force. So if you ever look at the car wheel, okay, so normally your car wheel have a rim. How to draw the rim? And the tires here. So if I cross section, this is the tires. There's a rim here. So you'll find that the weight were added to here and the inner part. Okay, the balancing weight. Okay, so it can be in these two plan. Okay, because the wheel we consider this axle is large. Okay, compared to the radius. Okay, or radius mean measure from here or the diameters. Okay. So you have time to look at the cars whether they have some counterbalance weight putting at the outer side and also the inner side of it. Okay? So that's why in this case, then your weight, your balance weight have a fixed R. Okay, in this case, right? Because your weight can normally is only put there. Okay. That's why the machine in the car workshop can easily tell them how much weight they have to add in. Okay, if you have time to go again, so you will find out that the technician in the car workshop will have to specify the rim size. So for example, now your rim size is 16 inch. You have to key in first. Once the machine measure all these forces, the machine will measure the forces here. Then you will be able, because you already specified the rim radius, so it can tell you how much weight to put in at either this plane or this plane, okay, at what angle. So this is on the wheel balancing, car wheel balancing. So it is always a good practice to first statically balance all individual components to reduce the amount of dynamic imbalance that must be corrected in the final assembly, and reduce the bending moment on the shaft. Okay? So what it means here, if there is possible, once you have this, you put a counter balance first. If you have this, you put another counter balance. So if then you put the measurement on the force at the shaft, then they will become neutral. Okay? But again, this is depending on whether you can your system allow you to add these two in or not. Okay? But unfortunately, most of the case, this is not favorable. This is not what your client want, or what the boundary of the system is allowed. So, for example, an aircraft turbine consists of a number of circular turbine wheels arranged on the shaft. The individual wheels are statically balanced before being assembled to the shaft. Okay. So this may be. Is every one of you know turbine? Yes, maybe we can look at some of the things here. So you can see this is one by one. Over here, this is many stage, right? So we have 1, 2, 3, 1, 2, 3, and then 4, 5, 6, 7. There's a lot, and this side we have a lot. So each of these, they will do a static balancing first. Okay. That's why previously I have a coursemates who graduated and then he become a turbine blade installer specialist. Okay. You need a specialist to install this blade. Okay. Because you cannot simply dismantle all this blade. Actually, each of it can be taken out individually. Okay. So when you take out this blade, you have to specify where are you taking out from each of these. That's why they need a proper trained specialized engineers to work on this with the high skill technician. You have to label one by one. So where you take from it and at which angle that should be installed on the shaft, right? Because they have been doing the balancing in the factory, right? So you have to put in one by one and build it. You can imagine how big is this turbine. So this is a generator, if you look at that. Okay. The principle is more or less same as the airplane. Okay. But the difference here is this one is to get the most power on the compressor and not compressor on the turbine side. Right. But for airplane, they are looking for how big is the thrust that you can produce. So this is turbine. Just now I mentioned the propeller. This is the one. So there is a propeller. Okay, this is a propeller type. I'm not sure how many of you taken Firefly before. I took once before, many years ago. It's a very interesting experience if you never take a small flight. right? I think you can try, right? It's a very interesting experience, right? Okay, so that is a turbine, right? That's why turbine is a, a very critical equipment over here. Or someone asked, question, propeller noisy. My experience on the Firefly is still okay, not that noisy, because when they design those propeller for airplane, they also look at the noise generation on the propeller. So now even like your fan, if you compare the fans nowadays, those branded one, and the fans that is maybe about 20 years ago, 20 to 30 years ago, same rotation speed, right? The noise is a huge difference, right? That is because now they also look into the noise generation from these fan blades, right? But for sure, this one, all this airplane, you don't stand outside. You are sitting inside the plane, right? Outside is too dangerous for you to be there. Okay, so one of the reasons why all these propeller and turbine have to be balanced, the reason is because normally uh, the rotating speed is very high. Okay, so if not mistaken, turbine we are talking about more than 10,000 RPM. Right? If not mistaken, maybe 10 or 20,000 RPM, but there is a turbine rotating speed. Right? So that's why if any small, that's how we look at the centrifugal force, mr omega squared. That's why if this is very high, you just add a little bit on here. Okay, so your force will go up, okay, a lot. Because some more the speed is with the square, okay, so that's why the impact is very high, okay, when you go to a higher speed. So electric motors, rotors, entire rotor imbalance must be counted in the two correction plane after the assembly, right? So consider the system of three lump mass arranged around and along the shaft in figure 12-3. So this is a figure. Okay? So we have three mass here, 1, 2, 3. So then we have to do, but these three, if you look at another plane view, they are not on the same plane, so they are on different plane. So then we can add two balancing mass to balance the system. Okay. But this one is mainly that they cannot be individually statically balanced. Okay. As I mentioned just now, if you can put this here, put this one here, this one here, then you not even need these two. Okay, you don't need these two. But the problem is now you cannot have this. Okay, so that's why you need these two to do the balancing. Okay, that's why sometimes you will look at the shaft end up must be very big in diameters because of this rotating speed as well. So that's why if you look at the turbine, they also put in a big shaft, right? Maybe we pull in again. So can you imagine how big is the shaft? Okay? If you look at this is a shaft. Okay? This is to prevent any bending happen during the rotation. Okay? Because the clearance in the turbine is very small, so you don't have the luxury to allow bending on the shaft. Once the shaft start to bend, then they will hit the stator on the turbine. Okay, so we look at so we have this diagram. So since we have so many mass now, we have 5 of it, including these two balancing mass A and B. So if we write the equation for summation of force equal to 0, so we can write it for m1r1 omega 1 square, m2r2 omega 2 square, m3r3 omega 3 square, mara omega square, mbrb omega square. So again, because everyone share the same rotating speed, so we can remove the omega. So again, I want to highlight here, this is actually the equation we are looking at. But end up after we removing the omega 2, so we left with this. Okay. Oh, I now I recall why I keep emphasize you must remember this. Because previously there is I think last 2 or 3 years ago, there is a student asking me why the force go like that. Because in your if you solve your center of gravity problems, you use very similar equation like this, right? But then your mass is going like that. Okay, so that is when you solve when you solve the center of gravity issue, your mass will going down like that. Okay, but the things now we have is you are there. Okay, there is we are looking at centrifugal force. Centrifugal force. Okay, that's why nothing about gravity we are talking about. So again, because we are in the dynamics, so we are not looking at the effect of the gravity here. Okay, that is your static problems again. So this is a formula derived from this centrifugal force equation, not the equation that we use. Okay, so there is one of your friend asked, why do we put 2 balancing weight instead of 1? The reason is you can't balance with 1. That is impossible for you to balance with 1. Okay? You can't solve it. Okay? That's why you need 2. Okay? You need 2 math. Okay? You can see now we have this equation, then we can break it into the x and y component again. Okay, but then we also have to solve the moment. Okay, the moment equation. Okay, so when we solve moment equation, one of the things you have to be careful or be alert is the reference point. Okay, where are you going to choose your reference for your moment? Okay, that's why when we always say summation of moment equal to 0. So here we always say summation of moment at O. Okay, so then we have to define where is O. So in this case, the books define O here. There is a reason why he choose there, because when you choose here, the force here, the mara omega square, will not appear. It will not appear in your equation. If you want to make your solution more complicated, you can choose your O here. Doesn't matter. But then your solution on your mathematics will be slightly longer, right? But if you want to shorten your equation, so you either choose here or you choose here, because this is an unknown. This is an unknown, same as this one. This is unknown, right? So if you choose here or choose here, then you can reduce one unknown in your equation. Then you can solve it a lot easier, right? So that's why here he chooses point O. So that's why we will not see MA in the equation. So you can see we left with only the MBRB omega square multiply, this is force, because moment is force multiplied with the distance from the rotation. So it's LB, and then this M1R1 omega square L1, M2R2 omega square L2, M3R3 omega square L3. So then again, we can divide everything with omega squared. So we reduce and then we come this equation here, right? So then we break into the x and y component again. So now we have 4 equations. That's why then we can solve for the 4 unknown. So what are the unknown we have? MA, RA, X, MA, RAY, MB, RBX, MB, RBY. So these are the 4. So always take them as a pair. We call it mass radius product. Okay. After that, then only we solve what is MA, what is RA. Okay. So don't try to solve the MA straight away from these 4 equations. Then you can do it. It doesn't mean it's wrong, but then it will be tougher, right, to solve this. Okay, so I will stop here. Then I will leave the example to the next week, okay? Next Monday, because now it's 1:55 already, okay? So there is some question, maybe not related one. Someone asked when the bird hits on the propeller will be damaged. So depending on what birds you hit, okay? So normally small birds, no issue. I just chop off the birds, okay? You can imagine that if you have a very fast spinning rope or cable, you throw anything in the rope, it's fine. Okay? Alright, compare because the speed will actually chop off the bird. Okay? Unless you have eagle flying in, then that's why airplane normally don't fly that low. Okay? So that is also one of the reason why airplane is not flying at the 200 meter from the ground. Okay? They will be flying far away, which normally birds will not fly at that height. Right? So if you look at your normal airplane, they're flying at the 40, Mexican 40,000 feet from the ground. So it's too high for the birds to fly there. Okay? That's why in the airport, then you have a special officer to chase away the birds. Right? There is such kind of job. If you're interested, then you can do. Helicopter, you want to chop the bird is not that easier because the blade is rotate at another direction. And also the same thing, helicopter also not fly that low. Okay. Okay, if no questions, other of you other can just leave the meeting. I will see you on next Monday. So thank you very much. Thank you for paying attention to the class.